Michael, how are you today?
I am good. The sun is shining.
Well, I have a question for you, just kind of leading into our topic of the day. So, do you plan things backwards or forwards? Do you start from the result and work out how to get there? Or do you start with what you've got and try to work out how to get to your desired outcome?
I am very much, I start with the result and work my way back. That's the hill I'll die on, is that is the best way to do things.
I think I'm the same. I definitely find myself reverse engineering things. It just, for me, it makes sense. So we definitely have that in common. And this week, we're actually going to be exploring why starting from the end and working backwards can sometimes be the best way to approach a problem. I'm Aubrey Lovell.
I'm Michael Bird.
And welcome to Technology Now from HPE. So, Michael, efficiency in AI has been a pretty hot topic for a while now, right? Everything from energy efficiency to the speed at which we get a result when we ask a question. But here's the problem, right? Things are often connected behind the scenes, and changing one thing can lead to unexpected consequences elsewhere.
Yeah, but presumably, Aubrey, this is something that could be prevented if it's thought of during the design stage.
Well, I mean, you'd hope so, but part of the issue here is learning how to try and predict unexpected consequences, right?
Yeah, and I also imagine that some things can't be decoupled either, like they're intrinsically linked within a system.
Absolutely. I mean, if a model requires lots of data to train and run, it's going to need lots of power too, and of course, the opposite is true. But the topic is, as you might expect, far more complicated than that. So, to find out more, I know you'll be excited about this, I was joined by John Frey, Senior Director and Chief Technologist of Sustainable Transformation for HPE. But before we get to John's interview, Michael, I believe you have something to tell us about.
Yes, I do, Aubrey, because we are going to take a look at one of the most famous examples of unexpected inefficiency in a system. Aubrey, it's my turn this week. It is time for Technology Then. Right, I want to start by debunking a common claim which states the QWERTY keyboard, the keyboard you probably have in front of you, was designed to be deliberately inefficient to slow typists down. It is said that this was because it helped prevent jams on typewriters for people who are typing too quickly. Now, are you a fast typist, Aubrey?
I would say I'm probably average. I don't know. I've never really thought about it. What about you?
You and I are of a similar vintage, I would say. I am not a touch typer. I am embarrassingly still like a little two-finger henpecker. Maybe some other fingers get involved occasionally, but generally I'm pretty analog with my typing. Well, we discussed frequency analysis a few weeks ago when we talked about ciphers, and we're going to be returning to it now because frequency analysis of letter pairings published by the University of Chicago, Illinois, shows that the most common pairs of letters are the following: TH, H and E, A and N, I and N, and E and R. And if you look at your keyboard, you can see that you can type all of these pairs incredibly quickly because they use different fingers. So if the keyboard was designed to slow you down, clearly wasn't designed particularly well. In fact, the keyboard was actually designed for telegraph operators transcribing Morse code, specifically American Morse code. So, for example, the letter Z or Z was shown as 4 dots, the letter S by 3, and the letter E by 1. This would make it very difficult to tell the letter Z apart from an S, followed by an E. By placing the letters next to each other on the keyboard, the operator could hover over them, and once the context of the message showed which was correct, they could then press the right keys. The problem with this is that while the keyboard was great for Morse code, it was not great for general typing. In fact, a much more efficient keyboard was designed in 1932 by a man called August Dvorak, which put the most commonly used keys in the same place and was designed in a both left-handed and right-handed formation to favour the most dominant hand when typing. And Aubrey, I've shared with you a picture of this, which we'll link to in the show notes so you can check it out. What do you think of this keyboard? All the vowels are in the same place. Don't you notice that?
I feel like this would hurt. Like my hands hurt looking at it. It's so spaced out though.
Without even typing on it, I sort of feel my wrists getting really sore. Anyway, a study by the US Navy in the 40s showed that it was significantly better than the traditional QWERTY keyboard, but unfortunately, by then, the market had already locked into the QWERTY model. This market lock-in has left us with a keyboard which works, but is by no means the best option out there.
But it really is just fascinating, right? That the inefficiencies actually arose because the keyboard was designed for a system, right? That we no longer use. So even though we now view it as inefficient, at the time, like we've been saying, it was the best model going. And that focus on efficiency really hasn't changed. However, the way people approach it very much has, right? So to find out more about that, I spoke with John Frey, Senior Director and Chief Technologist of Sustainable Transformation for HPE. And I started by simply asking him how efficiency is viewed in the world of technology.
When we think about overall technology efficiency, we've concluded over the 25 years of doing this work that there's really 5 levers, and we call them levers because they're interconnected: equipment efficiency, energy efficiency, resource efficiency, so all the things beyond IT, the cooling and power conversion and such. And those were where we started for about 15 years. But then we recognized the applications play a huge role. So we came up with software efficiency and our point of view on that. And finally, data efficiency. And although AI is very old, recently, of course, it's become a really hot topic. And as the topic started coming up, we asked ourselves, does anything about AI shift our 5 levers of efficiency or not? And what we came to the conclusion was, no, they're all still applicable. And in fact, some of them are even much more applicable, particularly as we start thinking about things like generative AI, where we have these large language models. The software efficiency piece takes on a disproportionately large piece. And then even when we start thinking about data efficiency, because so many of these AI solutions require a tremendous amount of data, how do we make sure we're using the right data and training appropriately and those sorts of things? The other thing we found from an efficiency perspective is often these new systems, when we think about agentic or generative AI, they take higher performing hardware, much more performance, yet a lot more energy consumption, therefore a lot more heat output. So we have to balance those nuances, the complicated algorithms, and as I said before, just a tremendous amount of data. So all of those have efficiency implications. And because those levers are interconnected, solving for one doesn't get the job done. You really have to look across. The other thing I would say from a slightly different take on efficiency is it's being reported that only about 5 to 10% of current AI pilots ever make it into production. So from an overall efficiency perspective, we have a whole lot of pilots going on, consuming a tremendous amount of resource, but yet those aren't making it into production. So from an efficiency perspective, we've got a lot of room to grow there as well.
Absolutely. And I know you mentioned the 5 levers of efficiency. We're talking about this broadly, but you did mention generative AI. And I kind of want to go back to that because it's something that a lot of people are hearing, probably most is like one of the hottest topics in AI. What is particularly challenging with generative AI versus some of the other types of AI?
The initial belief was the larger the model and the larger the data training set, the more accurate the model could be. These are very, very large models. They take weeks or months to train on hardware platforms that can be 100 million to over $1 billion. So they are very resource intensive. And by the way, once you've trained the model, it's only as good as the data that it had up to that training point. So if new information comes out that you want to incorporate in the model, you have to do more work there. The other thing that is slightly challenging about that is almost anything we know about the model efficiency, the model size, the resources it takes are forensic guesses looking backward. So the folks that develop the models generally do not release any of this information. The other thing that we're running into is models were continuing to grow, almost a logarithmic climb up in this quest for accuracy. And it was believed for a long time that that's the only way to get a more accurate model. And then we saw some small language models start coming out that changed that paradigm or challenged that paradigm. And all of a sudden, we're offering a fair degree of accuracy with a much smaller model. Yet the model growth continues. In fact, Uptime Institute published a paper on AI density that said, and I'm just going to read the quote, "Presently, there's no evidence of a profitable business model for state-of-the-art AI products costing hundreds of millions or billions of dollars to develop, or that scaling ... models another 10 times to 100 times would improve the financial viability of these offerings." Yet, even without a solid business case, there is no sign of the surge in investments in ever larger AI models slowing. That's a dynamic we've got to solve for. We're using a tremendous amount of resources for larger models when in fact their accuracy and their financial viability isn't proven at this point. So that poses an interesting challenge in generative AI, particularly when we're starting to see small language models that can be every bit as effective.
So does that mean people are going to have to choose between using large language models and those small language models, or are they able to work together to answer a question?
So we're already starting to see even the model developers start to shift that mindset from bigger is better to perhaps variety is better and use the most appropriately sized model for the task at hand. In fact, one of the latest models that just was released in the last few weeks actually auto throttles the input to the most appropriate internal model that it has. If you ask a simple question, it's going to use a much smaller model to answer that, partially to get the asker a really quick answer, where some of the more complicated questions take longer to produce the output. So even from a consumer use perspective or a user satisfaction perspective, being able to use smaller models sometimes to answer those simpler questions makes the user happier because they ask a question and get an almost instantaneous answer. So all of that wraps together to say, how do we balance efficiency, user satisfaction, the financial viability of these models? And that's still being solved for as we go.
Absolutely. And I think to your point, right, you're seeing obviously there's a long way to go and there's gaps to be filled, but what we're kind of seeing is that shift as well as it being so accessible just to on a normal consumer base and normal laptops. We were kind of talking about different types of AI, and one word we keep hearing over and over again is agentic AI, right? So as this becomes more common, what is the difference between agentic AI and tool AI?
Yeah, great questions all. Agentic AI is a term that you hear a lot of, but a lot of times people don't understand what it is. And very simply, it's an AI tool that can do multi-step problem solving or multi-step processes. If you think about the way most of us interact with, say, a large language model or a generative AI model today, we ask a question and get output. Then we say, refine your answer, or that's not what I was looking for. And we ask another question. So it's input, output with a human involved every step of the way. Where agentic AI can actually take an input and then do multiple things. And in fact, sometimes even take an action that doesn't involve the human being involved in that. And because it can do that fine tuning, it can get more nuanced answers and can learn from experience as well. So agentic, part of the reason people are excited is because it allows the intelligence to do more things. But let's remember, behind all of this is a mathematical or a set of mathematical equations that are happening. There's not actually human reasoning behind the scenes. These are still tools that involve some human interaction.
And what does that look like from a sustainability perspective, John?
So when we use agentic from an efficiency perspective, you want to put in things like guardrails, give the tool itself some parameters to stay within, for example. Think about the unintended consequences and take those out of the equation if you can. So a great example of this is Antonio Nearly, a AI solution that we built to interact with customers at customer events and things. And it's an avatar of our CEO, Antonio Neary. And part of when they first trained that system up, they trained it on every press release that HPE has ever released. Well, what does every press release have at the bottom of it? A legal statement. So when they were first working on Antonio Nearly and allowing it to actually do some agentic types of things, one of the guardrails they put in as they learned from experience was tell it to ignore that statement at the bottom of every press release, because it gave that statement the same weight as what was in the press release, which was completely unintended. But that's the way press releases are written.
That's the sort of thing you just don't think about unless you've made that mistake before. So those guardrails are really important. And I guess if you're putting those in place to stop it wasting time considering material which isn't needed, you're also improving the efficiency of the system, right?
So from an efficiency perspective, some would say, well, actually, if the tool can take multiple steps on its own, you're generating more resource use by that inference process again and again. This self-diagnosis and intervention capability of agentic AI is partially where we're seeing the return on investments really come to play, because we can solve a much bigger problem before it ever happens. Or in a customer satisfaction perspective, if we can take some action and keep a problem from occurring from a customer perspective as well, there's huge financial benefit to that as well. So for us, then, how we've learned to look at AI efficiency, and particularly as agentic has become more prevalent, is think about the entire solution. Because often the customer buys an optimized piece of hardware and they put it in a data center they hope is optimized. And then they buy an application that they hope is optimized. And so we're optimizing the piece parts, but that doesn't necessarily tie it all together. So we're teaching our developers internal to HPE, and also suggesting to our customers that they design AI solutions from a solution perspective and understand the interplay between the pieces. You can have a very inefficient solution that has optimized pieces if you're not using the pieces effectively. We're helping them think about all those implications, because as these solutions become more and more common, we need the license to operate in the areas where customers want to run these solutions. So we've got to think of this optimization and efficiency from the beginning and then all the way through.
Got it. It's almost like, when you think about city planning, right? Or when they're building roads, you want to build a road and add lanes for the predictive population, not the population of today, right? So I love that there's so much thinking and the solution built up front of what that could look like to mitigate all of these things, and also free up resources as well.
Absolutely. And, one of the other challenges is over 80% of the data that people want to train these systems on is unstructured. So how do we get that data that wasn't in a database or in a structured format and get that into solutions so we get the benefit of that knowledge, but get past some of the challenges of dealing with unstructured data? So again, if you think about that from the beginning of the design, you can adapt to that, but that's another challenge that comes into play in these systems.
True. And I think there's, another side of this too. I mean, it's exciting that agentic can kind of have its own personality and do these things without necessarily a human being involved all the time and make its own decisions. But you have to kind of wonder as well, how do we ensure that they're doing what they're supposed to be doing and not misbehaving?
Part of what we have to acknowledge out of the gate here is that we're on a huge learning curve. So one is anticipating the unintended consequence, and history can teach us a lot about unintended consequences as well. And where there are life safety implications or environmental implications, you put more guardrails on those things so that you prevent that, or you get a human involved in an intervention. And often these agentic systems can go to some point and then a human's got to get involved again. So one of the things that HPE has been very focused on, and I think Kirk Bresnicker has been on this podcast before, talking about, is the responsible AI attributes that go hand in hand with efficient AI. We tell our customers you need both. You have to have sustainable AI, but it's also got to be responsible. And so don't decouple those from one another either. So focus on the efficiency of the solution and then on the efficiency of what you can do with the solution to drive new efficiencies as well.
Okay, so I do have one more question. Can you use AI to make itself more efficient, right? I think we have to ask the question, right? If they're thinking on their own and they're doing all these things, can they essentially improve themselves?
Absolutely, yes. And it's happening today. And a great example of this is one of the early adopters of digital twins that I know has been talked about on the podcast before, is for data centers itself and data centers running AI workloads. And there's a variety of reasons for that. Some is there are some parameters you can set and allow the agentic tool to control cooling and other attributes within that itself. And so it can even predict things. The other thing that we find is often for some of that mechanical equipment, if you bring it up to temperature slower, it's more efficient than if you rapidly have to bring it up to temperature. So we can even predict times looking at weather patterns and things when you're going to need additional cooling and bring it into bear slowly. Or if you're talking about shifting workloads or adding workloads, what are the implications of that in the data center environment that's already there? And using a digital twin, you can run a variety of those scenarios to operate more efficiently. In fact, we have customers that are doing that today. And that's a big part of HPE's digital practice or digital twin practice and our solution set. So that's a great example of using AI to make AI more efficient.
Always love having John on the show. I always think he's got such wonderful explanations. I don't know about you, but like one of my big reflections from that interview was I've never heard of the phrase small language models before. Had you before that interview?
Not really. I know what he was talking about, but I just never heard it in that context.
The concept of using the right size model for the task at hand, I think that's what John said. It sort of feels a bit reminiscent of the way that the processors in our computers have changed over the last couple of decades. And certainly laptops from some manufacturers have like individual parts of the processor for specific tasks, which relates to what John was saying. You know, you have an AI model for a specific task at hand because it's a way more efficient way of doing it. Whereas processors from 20, 30 years ago, it was just about pure grunt. Like, how much power could you shove through this thing? And that meant that like laptops would burn through their batteries very quickly and would run very hot. Whereas nowadays, laptops don't burn quite so hot and they can sit on their batteries for quite a while. So I thought it was quite fascinating because I think it feels like we're maybe in that stage of AI.
For sure. And I think we touched on that a little bit, right? Where we were talking about how it's so consumable now. Like there was a time when AI could only run a certain way on a certain type of, massive computer and only accessed by so many people. And now it's like, oh, everybody has access. It is super scalable. And these solutions are kind of bespoke to what you need and when you need it.
And I think that the point you made at the end about using AI to make itself more efficient, and John's point about like predictive cooling or predictive workload optimization, it makes sense, but there is also an element of like, well, yeah, of course, that makes so much sense to use AI for things like that. Like the things that AI is good at, let's use it for that.
For sure. And I just really love talking to John, right? I mean, he's such an interesting guy. He's done so much. And, he's really been in the industry for a really long time. So I thought to close out the conversation, it would be really interesting to finish up with the major AI breakthrough he would love to see in his lifetime.
I think there's lots of opportunities to use AI as an adjunct to bridge existing gaps. I think of folks that have mobility challenges or even neurological challenges. And how do we use an AI tool to allow them to interact with their environment around them in a much more natural way? Huge progress has been made over time, but really opening those opportunities. How do we do things like explore space when the number one challenge is how do you get a human to live in a space environment? My early career, I worked for NASA during the days of the shuttle program. And so how do we unlock some things like that pose great opportunities perhaps for new materials to be developed or whatever, that today the challenge is we have to have the human involved directly. Perhaps AI can enable us to solve some of those challenges as well. I don't even think we've thought of all the uses that we could use AI for from a productive perspective. Again, I think the responsible AI has to be hand in hand with the efficient part there, but I'm excited to see where it goes.
That brings us to the end of Technology Now for this week. Thank you so much to our guest, John Frey, and of course, to our listeners. Thank you so much for joining us.
If you've enjoyed this episode, please do let us know. You can rate and review us whenever you listen to episodes. And if you want to get in contact with us, send us an email to technologynow@hpe.com, subject title line, to the moon. And don't forget to subscribe so you can listen first every week.
Technology Now is hosted by Aubrey Lovell and myself, Michael Bird. And this episode was produced by Harry Lampert and Izzy Clark with production support from Alicia Kempson-Taylor, Becky Bird, Alyssa Mitchery, and Renee Edwards.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green. And our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett Packard Enterprise. We'll see you at the same time, the same place next week. Cheers.
Cheers.